All right, hello and welcome to Gears of Resistance number 4. Very belated on a very late Sunday. Let's see here, March 22nd. Yeah, I think so. So, gotten some feedback, mostly positive, mostly pointing out that this is a fairly amateur hour production, and that is exactly true. Very much so. So, but there's seems to be two types of requests. Mostly looking at how do you do your process, how do you do your design, how do you do your work, how do you do your job. Seems to be half the questions, and that includes like what tools do you use, and then the other questions are tutorials and explanations of theory. And I'm actually getting a lot of amateur radio questions, which I think probably ties in because I'm a ham radio guy. And that's something we've talked about before. So we're going to try to go that route and keep with the fundamentals and the theory for now. And then tie this into some projects later. And then as we do the projects, do the how-to. And my cat has now joined us as well. So so far we've discussed the basic theories of voltage, current, resistance. We talked a little bit about impedances, reactances, which is basically frequency dependent resistance that appears in capacitors and inductors. And we talked a little bit about that last week. So I wanted to kind of take that and a little bit on some power discussion and try to bring those two together. And we'll see if this works. This is all an experiment in teaching electronics. I've seen a lot of different ways. I've seen some really good ways to teach electronics, and I've seen some not so good ones, but I've never found the one that perfectly makes sense. So I'm trying to basically figure out my own way, and you're kind of like the guinea pigs of figuring out how's the best way to teach building blocks on electronics. But no, London, as my cat tries to jump up and stare down the set. So with that, without getting the microphone in the way too much, and let's see if we can bring this in without. Last time I got a lot of comments also that there was a lot of glare, and that was true. And I think I figured out the right angle to get this. All right. So let's go back to where we started the other weekend. Let's just draw a battery. A resistor. And to show that we're going to have like an external load, what I draw is little circles. And then, and again, some parts of the world, instead of showing a resistor, they show a little square box to indicate also for impedances too. So to show that this particularly, it's not like it's a black box, it's just a way to show impedance. So these can sometimes be used interchangeably. Sometimes they just mean resistance. Other times, I think more appropriately, they're supposed to indicate there's an impedance, which is again a complex resistance that accounts for both the resistive property of a element as well as its reactance. And we'll talk a little bit more about that. But for now, the question is, let's assume for a moment that this is a 100 ohm resistor. This is, I don't know, let's do a 5 volt source. So the question is, what size of resistor do I need to pick to get maximum power transfer? And then remember, power equals voltage times current. So if I want to get max power out to my load, we'll go at R sub L, and I know that my internal output impedance is 100 ohms and my source is 5 volts. What size resistor do I need to put here to get maximum power. Now realize, oh, I'm getting that glare again, aren't I? Let me go back that way. There we go. I'll say that for the rules. It's not always true. Sometimes this is ideal is not to have it exactly. Well, I'm giving away the secret anyway. Let's hold off on that. So the question is, I'll give you even choices. Should R sub L equal 1 ohm, 100 ohms, or 1,000 ohms? So, when the thought of it is, okay, if I want maximum power, maybe I should have the smallest resistor, and that would give me the most power, maybe. Well, if I do 100 ohms, that's my internal. How would I get max power? But maybe that's, well, 1,000 ohms, that's a bigger resistor. So how would I get max power from that? So hopefully you've got an answer. But let's go through and figure it out. So I can't remember if I used the term Kirchoff's voltage laws and Kirchoff's current laws in the first or second episode. But if I didn't, let me correct that now. So Kirchoff's voltage law says around any closed loop circuit that the sum of all the voltages, the gains and the drops, will equal 0. So again, we'll say this is plus the minus. I'll go around this way, plus minus, plus minus. So as I go through this closed loop, and that's actually going to be, that current is going to be current I go up 5 volts. I got to drop some voltage across this resistor and some voltage across this resistor. And when these 2 voltage drops are done, they will have dropped the entire 5 volts. So it could be 3 volts and 2 volts, 2 volts and 3 volts, 4 volts and 1 volt, some combination. I have to drop this full 5 volts. So that's the circuit. I'm going to minimize it here real quick, and we'll start doing some calculations. And these are real basic ones. And again, the target audience here is not double E majors. It's, maybe if you are starting off as an undergrad. And this isn't even really, this is, again, microelectronics, microcontrollers, real small voltages and currents. Things change when you get more complicated. You start going into the high voltage world or some other stuff. So anyway, let's real quick so we don't forget. It was 5 volts source, and the little plus, little circle, the plus and the minus is another way to denote a DC power supply. I had a resistor. We'll give that one, say, R1. And then I had another resistance out here, which is my load. And so my question was, what happens when R load, and this R1 is 100 ohms. So when R load equals 1 ohm, 100 ohms, or 1 kilo ohm, let's look at our current, and then let's look at our power, which again is the voltage times the current. Okay. If I sum up the 100 ohms plus my load of 1 ohm, my total resistance, actually let's put a space for that, R total, R sub TOT. I have 101 ohms, I have 200 ohms, and I have 1100 ohms. Just 2 series resistors. The resistance, total resistance, is the resistance summed together. Okay, so current I equals V over R. And again, my mnemonic is the Indian sees the vulture over the rabbit. That's how I remember it. It's just a way. So let's move this all over just a little bit. All right. So it's 5-volt source over 101 ohms. My current is approximately, let's see here, 1, 2, 3, 49.5 milliamps. Did I get that right? 1, 2, 3, yeah. All right. What happens if it's 200 ohm? Again, 5 divided by 200. It's about 25 milliamps. And what happens when I drop this 5 volts over 1100 ohms? I get 4.5 milliamps. Draw that a little bit nicer. Okay, so you already see, okay, so as the lower my load resistor is, I'm pumping out more current. And as my load resistor increases, I'm getting less and less current. So far it makes sense, but the question isn't the current or the voltage, it's how much power am I getting. So power, again, equals voltage times the current. And another way you can substitute that is, again, we'd say we know what V is. Take Ohm's law, so V equals IR. You could substitute that for V, so power could also equal I squared R. Or if you knew the voltage, substitute it again. Let's say we knew the I, could substitute that over here. So it's power is also equal to V squared over R. All right, so let's look at our load resistor. And in the case of a 1 ohm load resistor, I have 0.0495 times, squared times 1 ohm. So I'm getting about 2.4 milliwatts. Okay. Let's go down. I'm going to 25 milliamps for the 100 ohm squared times 200 ohm resistance, or excuse me, the 100 ohm resistor. I'm just carrying, again, the power across this resistor here, not the total. That comes out to be 62.5 milliwatts. Okay, that's a sizable, that's an order of magnitude more power. Still, though, in the grand scheme of things, not a lot of power, which is good because we're small voltage kind of guys and gals. All right, 0.0045 squared times, oh wait, let's think here, man. That's a really big resistor, 1K. So 0.0045 squared, is that going to give me is this going to be 100 milliwatts? Maybe 200 milliwatts? Let's see what it comes out to be. That's interesting. It only comes out to 20 milliwatts. Oops, let me get that out of the way. Drop the mic. All right, so when my load resistor is 1 ohm, I'm getting 2.4 milliwatts across it. When it's 1,000 ohms, I'm getting 20 milliwatts. But when it's 100 ohms, when my load resistor is 100 ohms, which means it's matching my internal resistance, my R1 up here, I'm getting 62.5 milliwatts. And that's the case. That's the rule. It's the max power transfer occurs when my load resistance, or my load impedance, because we're going to start bringing these two worlds together, the complex, in the world of impedances, but it holds true for the resistance as well. When my load resistance and my internal resistance they're the same, I get max power transfer. So things like, that's why, and it's not true exactly for speakers, people use as an example. Some of my research, having a much lower resistance for my source, my driven element, it's like the last stage of an amplifier before I hit the speaker. You actually do want that lower, but where it does come into matter and where people have been asking questions is with antennas. So from the radio to your antenna, you want to have those impedances match. And now you can kind of see why I started wanting to talk about last week reactances, and why I kind of been alluding to the whole thing we're going to discuss with how does this change, or how does this vary a little bit when I'm dealing with complex signals, so not just straight DC. But I needed to get this laid out first. So lesson learned: load resistor equals my internal resistance, my source, my output impedance. I will get maximum power transfer. And that's usually what we're aiming for. We're usually trying to get the most power to our load. And as an amateur radio guy, that's my goal, is always to get as much energy dissipated out over the antenna as possible. Again, when you start dealing with, radio frequency currents, again, this changes with the fact that there's reactances, but this is the basis. So just to make this even more complicated, so we talked about that there's, again, there's resistance, there's reactance, and there's impedance. So it's kind of drawn as this triangle usually. So there's resistance, there's reactance, and again, there's inductive and capacitive reactances, and then there's impedance. All these are measured in ohms. Now, you have to take into account that, again, at alternating currents, voltages and currents aren't always necessarily what's called in phase. So in other words, this is going to go real. So I have my amplitude, either, again, voltage or current. Actually, we'll change the colors up here. Of course, that just happened. All right. So we'll do voltage in red. We'll do current in blue. So in DC, voltage and current are in phase. They're not changing. But it's possible with alternating AC signals that the current and the voltage aren't in phase. So in other words, the current passing through the system, through your circuit, could be leading or lagging the voltage changes. Now, we'll probably do some more we'll do some more deep dives on that. But the point is, for today's kind of overview, is that because we have these different types of resistance, reactance, impedance, therefore voltage and current can flow differently. And remember, we talked about, again, the four fundamentals being voltage, current, resistance, power. That where did I want to go with this? There's different types of power as well. So it stands to follow that there's different types of power, or the way we they're not different types, it's just different attributes of the signal. So there is real power, which is what we've been talking about thus far and measured in watts. There's also, let me change this up here. In the reactances, there's reactive power. That's usually measured in VAR or VARs. So unlike impedances and resistances and reactances, which share ohms as their unit of measure, power, it's different. And so the complex, so resistance is just what, let me think, how would I put it? The way we use resistances is for things like measuring your electric bill, or for figuring out the heat load of a circuit. So the heat load it generates. This is power that gets dissipated by the circuit. And that's the money, that's the power you spend money with. Reactive power is the power that gets stored in the system and then released back into the system. So motors, capacitor banks, generate or consume reactive power. So this power doesn't dissipate into heat. It's simply stored and returned internal to the circuit. So it's just like impedance is this complex arrangement between resistance and reactance. It's not just the sum. It's there's some it's not that straightforward. There is the equivalent power, and that is what's sometimes called apparent power, and it's measured in volt amps. So, and actually, so we talked about here earlier that there's this different potential for a different phase, or a phase difference between the voltage and the current. And the angle, and again, hopefully if you've probably done maybe some geometry, maybe some college, high school math, basically, you can measure that angle between the voltage and the current signal, and that angle is called the phase angle, and that's represented down here in this power. They call it the power triangle. So here's the real dirty secret. So we've been talking about power equals voltage times current, and like I said, for DC that holds true. The reality of this, if you write this equation, the full the whole equation is actually power equals voltage times current times the cosine of the phase angle, which is basically, let's say we're talking about our power here. It's my real power. It's the ratio of my real power over my impedance, or my apparent power. And that's that is cosine phase angle. So we're not going to get too much into that. What the point is in the fact that, or when it's true that it's DC, current equals, the current is in phase with the voltage. Therefore, this phase angle, or this would go to 0. So again, my apparent power would equal my real power. And so anytime you take the cosine of 0, the cosine of 0 goes to 1. So power equals voltage times current times 1 can be just then reduced to power equals voltage times current when you're dealing with DC. So again, not to make this too complicated, I don't want to go into the math behind this yet, but my point is to take this concept that I have real power, reactive power, and apparent power. And the different thing with apparent power is we use apparent power to do things like sizing our wires. And again, when you're in the when we're in the electronics world, the small voltage, small signal, this doesn't matter as much. When you're dealing with, say, power utilities, this really matters. And it's also for sizing our circuit breakers. Because yes, I'm pulling this power in off the grid. It's getting dissipated as heat. But say again, if I'm dealing with a lot of motors, I'm producing and consuming reactive power. So there are times when as I'm going through the cycle, that I'm dumping more power into the circuit than I'm consuming, or that I'm burning as heat. So my wires have to be sized to handle both the real power and the reactive power that's going through my system. Whew. I don't know if I explained that as well as I would have liked, or for the purposes that I'm trying to get at, did I explain it the way I wanted to? I'm not sure. For most of us in the small signals world, where this will kind of start to matter is, again, if a lot of people are starting to do things with the radio, and especially ham radio, amateur radio, where you could deal with 500 watts, a kilowatt, which to some of my buddies who are electricians, they would laugh. But for us small signal guys, that's just enough power that we want to deal with. So if you take in the first thing we talked about, which was max power transfer, and you take this stuff that we just talked about, the reactive power, apparent power, and real power, and we're going to combine these here as not to talk about it today, but to kind of you figure out where we're going. And that is to use the example. Again, since I'm getting a lot of ham questions, which way are we going? This way. So I have my radio, right? And we'll draw that as a little black box here. And over here I have my antenna. That's my little symbol for it. And I'm also going to have my coax 50 ohm cable, 50 ohm coax. So here's the interesting thing. If I were to take my multimeter, say my little multimeter here, my little plus, my minus, and I go in here and I hook up positively to one end of my 50 ohm coax, and I hook up my other end to that side, guess what I'm not going to measure? I'm not going to see 50 ohms. the cable itself is not actually 50 ohms. It deals with the fact of, again, there is the property of reactance and impedance. That resistance is one part. It's the part that dissipates heat, but there's also the reactive part, and that combination together, you get an impedance that's frequency dependent. In other words, my resistance, my impedance that I see depends on the frequency of the signal that I'm passing. So as a amateur radio guy, going back to the idea that we just talked about max power transfer, that on my antenna here, I want to be dumping as much energy out into the ionosphere as possible. To do that, I need, and as you could probably guess, to match the impedances of my radio, of my transmission line, which in this case, again, is our coax, and my antenna. So depending on what frequency I'm operating on, say I'm doing the 20 meter band, say I'm on like 14.25 megahertz. Well, my guts of my radio can adjust to always ensure that I see an output impedance of 50 ohms for that frequency. I'm picking 50 ohm coax. Now there's also 75 ohm, but that's more used for like your inside of your house for cable television. And we can talk about wire ladder. And we can talk about even why is 50 ohms used? Why isn't it like 20 ohms? Why isn't it 100 ohms? And it goes back to kind of one of those things that it's arbitrary, but there's some math behind it. So there's two things. There's max power transfer, but there's also signal strength. So at lower than 50 ohm line impedance, I'm not getting max power transfer. If I'm above 50 ohms, then I start to cut down on my signal strength, my voltage level. Now, again, because we are concerned about max power transfer, but we're actually more concerned about getting because the voltage, the signal of our voice, it's not huge voltages we're dealing with. So basically 50 ohms is kind of the sweet spot between getting maximum power transfer without inducing so much, without basically killing the signal, without killing the voltage signal. There's a lot more history and a lot more math behind it, but in a nutshell, that's it. 50 ohms is kind of like that, at one point I lose too much power, and another when I'm starting to get too much resistance and my signal dies. They found the sweet spot occurs around 50 ohms. Again, the 75 ohm that you find in your cable TV, because they're even less concerned about power transfer, and they're really concerned about getting the signal strength through, the voltage signal. That's why they went to 75 ohms, because it killed the power, but it was better for the signal strength, the voltage strength. So, there's the signal, and everything has grounds. Same thing with our antenna. Let's get rid of our little voltmeter here. Little multimeter goes away. So 50 ohms, that's what you're going to buy. You're going to buy 50 ohm. If everything was perfectly matched, it doesn't matter how long your wire is, but when you have any sort of, and nothing will ever be perfect, then the length of the wire matters. And then, of course, on the antenna side, let's see here. Let's say, like, I use a lot of times I'll do a horizontal dipole. So basically, you have like two inductors. The signal comes in. I have two inductors. Then I have the whips that come out, and basically, I can adjust the inductance and therefore the inductive reactance by shortening and lengthening the number of turns on my antenna, and then I adjust the length of my whips. And the whips, by the way, what they introduces the capacitance, because you have to have it looks like well, you would say, well, we talk about the circuit has to be complete. Well, if I have two pieces of wire that aren't connected, how's it a complete circuit? Well, the atmosphere and your two whips act as a capacitor. So that's how you get your resonant circuit. Because a resonant circuit, you need a capacitor and you need an inductor. That's horrible drawn, but oh well. Go with me here. So to get a resonant circuit, sometimes called an LC tank circuit, in theory, if there was no resistance and things were perfect, I would oscillate back and forth forever. I would get push current through the inductor. It would store on the cap. The cap would then discharge and then go through the inductor, create a magnetic field, and that energy transfer would happen forever. It's not reality because there's resistances, so eventually the signal dies out. But for our purposes, what I need to do, again, going back to the point of max power transfer, I need to get my antenna to look like it has 50 ohms of impedance. And how I adjust that, I can shorten and lengthen my whips, and I change where I tap on my inductor, my coils. So by changing my coils, I adjust the inductance, or the inductive reactance. By changing the whip lengths, I'm changing basically the capacitance. And again, because it's frequency dependent. So when I'm operating on 14 megahertz, certain lengths will work. If I drop down to, say, 7 megahertz, I would have to go out and physically, if I was looking for, perfection, I would have to go out and adjust the length of my whips, change the taps on my coils, to get, again, so that my radio would see 50 ohms on the output, 50 ohms on the transmission line, and 50 ohms out at the antenna. And therefore, I would hopefully be heard around the world. That is what I wanted to kind of discuss tonight. Because I'm trying to walk this fine line between purely theoretical and everything purely academic, and just teaching nothing but rules of thumb. So I'm trying to teach little theory, little applied, and hopefully it will come fresh in my eyes how this should be taught. So with that, again, because you're my guinea pigs, feedback. Hit me up with feedback. And what am I not explaining? If you're a professional, if you know how to, if you teach this stuff, you've got expertise, please share. If you are someone who is trying to learn, even better, in my opinion, what more do you want to know? And, there's things here kind of too much. Is it not enough? Are we going too fast, too slow? Is the way we're breaking this up not making any sense? And again, you have to kind of look at these as a continuation, that you have to go back to the episode 1, watch from there, and move forward. But that's it for tonight. It is getting late, and I need to get to bed. So if any questions, head over to steampowerpodcast.com. There's links to everything else we do, and you can send an email if you want to send your comments privately. I don't mind public comments too, even criticism. You can put those in the links on the YouTube page. The comments, leave comments on Google+. That seems to be the most things I get is through email, and that's fine. I would like to have more public discussion because I think it benefits the group as a whole. But if you want to just send email, that's cool too. And if you're listening, it's you can send it to Mike at steampowerpodcast.com. That's the email address. So with that, next week we'll be up with a new Steam Power podcast, and then 2 weeks we'll be back with excuse me, a new episode of Gears of Resistance. Will be number 5, which usually gets to the point where I start figuring out this is something I'm going to continue to do, or if it's something I'm just going to end with dignity. I think we'll stick with it though. Next week we're going to take a break from the theory and talk about some tools and setting up a workshop, because again, that's the other big bucket of questions I'm getting. So we'll talk about that. And I got some new tools here recently, and they'll be cool to show what you can do with them, and how and then also why you don't need to start with tools, fancy tools, straight off at the beginning. So we'll do a little bit of that. We'll do a little show and tell at the of the lab here. And with that, thank you all very, very much for listening. And until next week, stay quirky.